SwayamPrabha. Digital India. Educated India.
In this lecture, we will use MD simulation data to measure certain structural qualities or structural quantities of the system. In the last few lectures, we have been discussing how to use MD simulation data to measure certain thermodynamic properties. The first set of properties were simple thermal averages, which are nothing but the first derivative of free energies, which includes pressure, energy, etc. Then subsequently, we discussed about certain thermodynamic variables, which are known as thermodynamic response functions, which could be expressed as a second derivative of free energy with respect to measurables. This involves heat capacity, thermal expansion coefficient, etc. In continuation with such a discussion, today we will discuss about how to analyze structural features of a fluid. So, what do I mean by structural quantities or structural information? If you think about a liquid structure, you can imagine it is as a dense collection of particles, in this case atoms or molecules, which are shown as simple circles here in 2 dimensions, but in 3 dimension they are supposed to be spherical systems. And so they are very dense in the sense that you see many neighbors around, but there is no particular order, translational order in such a system. You see that the molecules are hitting each other and moving apart, and then there is a dynamic motion of atoms in the system. So, if you target one particular atom and then you look around, and what you see is that you see a layer of first neighbors. This is called first coordination shell. Okay, there will be certain number of neighbors which are closest to the tagged atom, and after you go a little farther away, you will see a second set of neighbors at another particular distance. So, the liquid structure basically tells us that what is the local arrangement of atoms in a given system. Similarly, if you look at a crystalline structure or solids, this is also very dense, but apart from being dense, you also see that the atoms are located in lattice points and with a very long range periodic order. So, if you look at any one particular atom and if you go in any particular direction, you see a very systematic periodic arrangement of neighbors at a very specific locations. So, what we are intended to do in this approach is to find out what kind of atomic arrangements or molecular arrangements exist when you simulate a system. So, you construct when you want to study a system in MD simulations, the first thing to do is to set up a potential energy, and then you approach by solving either MD technique or Monte Carlo simulation technique, and then you try to study the system at equilibrium. And once the system has reached equilibrium, you want to find out what is the local structure, local order of the system, which could be either liquid like or crystalline like, or it can be even in a gaseous state as well. So, how do we identify and characterize equilibrium phases in simulation? So, that is the question that we want to ponder here. So, if you think about how do we really characterize local structure of a system, what I mean by a system is a collection of n particle interacting system. As far as crystals are concerned, we know that we use lattice groups and lattice constants, and then we specify what is the local order, periodic order in a crystal. But when you go to liquids and gases, such lattice groups or lattice concepts cannot be used because liquids and gases do not have long range order like the crystals. So, how do we go about characterizing liquids and gases in a simulation? So, one hint you can get is by looking at how we started modeling our system. If you recall, the total potential energy U is something we wrote as unibody potential and then pair body potential. So, most of the properties of the system are governed by this two body interactions. pairwise interactions. So you might think that what would be the distribution of pair distances in a given system, because that is the most important parameter in describing the potential energy of the system. So a naive idea to look at local structure would be to find out what would be the distribution of pair distances for any pair of particles. Okay, in a system of n particle, you pick up 2 particle and see there is a distance between those 2 particle, and then you see what is the distribution of such pair distances, and that has relevance to what is the most probable energetic states and which will be more close to an equilibrium system. So in other way of saying the same thing would be, what is the likelihood of finding a pair of particle at a distance of r. So if you are able to get such an information, then we can get what is the coordination number, that is how many number of neighbors are there in the nearest neighborhood, and what's the second nearest neighbor, etc., etc. Such information can be obtained by simply looking at pair distance distributions. So we are going to use such an approach to characterize and identify local structure of a fluid system. So now we want to have some mathematical expression to get this pair distribution function. So this is something rigorously can be defined using our configurational integral or partition functions. We may be interested only in the final result, but if you are interested to know where, how and where this expression comes from, we may want to just follow this particular approach. So when we talk about structural quantities, we are talking about only the positional correlations. We are not interested in the momentum correlations or velocity distributions. We look at only how particles are arranged, and this can be averaged over time or it can be averaged over ensemble. Okay, so we are looking at only structural quantities which are only functions of coordinate spaces. So because of that, we will take only our configurational integral. You can see the momentum is not there. We look at only a configurational integral, which is basically a 3n dimensional phase space. And in this case, we are talking about NVT ensemble. So the partition function goes like integral over all the coordinate space weighted by a factor of exponential of minus beta u. So what this integral here means is basically integrating over all possible positions of the first particle, second particle, third particle, and go all the way up to nth particle. Okay, that's what this drn integral means. So now what we can do is we can write this partition function or the configurational integral into several hierarchical distributions. What I mean by that is, you could think of writing this configuration integral as a hierarchy of many smaller functions. Okay, in other words, suppose if you consider this rho 2. Okay, so this is not rho square, it is rho 2, this is order 2. This basically tells you what is the probability of finding a particle at position r1 and another particle at r2 after integrating over all the other rest of the particles. Okay, so let me show this pictorially. So imagine you have a system of n particle. Okay, so now I am going to fix one particle here and another particle over here. Okay, so their positions are now frozen. This is r1, this is r2, and all the remaining n minus 2 particles are allowed to sample the entire phase space. Then you ask, given that 2 particles 1 and 2 fixed at locations r1 and r2, what is the likelihood of finding such a pair of particles in the entire system? Okay, so that function is given by this rho 2. The way you do that is, you fix 2 particle and then let the other particle move around in the entire phase space. Okay, so that means instead of doing integral over the entire particle, we will keep 2 of them chosen and integrate over the rest of them. So mathematically it can be shown as this: rho 2 is integral over all the n minus 2 particles. I am doing over only n minus 2 particle because the 2 particles are already fixed in certain distance, that is as a function of r1 and r2, and then divide by the total integral, that is the configuration integral. So this ratio will give you what is the distribution of distribution function for fixing 2 particles at a given distance. And you also see that there is a factor of n into n minus 1. This is because these particles are indistinguishable particles. I have the choice of choosing the first particle out of n particle. So, we have a factor of n in choosing first particle. Once I have chosen the first particle, the remaining are only n minus 1. So, I have to choose a second particle only from a population of n minus 1 particle. So, that gives a combinatorial term of n times n plus 1. So, that many number of ways you could actually choose 2 particles out of n particle. Okay. Then you have this integral like I said before. So, now you can ask what this function look like for an ideal gas, because we know that how to solve for ideal gas this exponential, because for ideal gas potential energy is 0. So, we can analytically solve this function for ideal gas. So, in order to do that, first we take this integral, which is configurational integration over n minus 2 particles weighted by exponential of minus beta u divided by the configurational integral. So, when I look at this, so this term is 1 for ideal gas and this term also 1 for ideal gas. So, we are essentially integrating over all the particles n minus 2 particles on the numerator and n particle in the denominator. So, the integral over the phase space of n minus 2 particle will give you a volume to the power n minus 2, and whereas in the denominator integral over n particle phase space will give you v power n. So, thereby you get 1 by v square as the value for the ratio of this integral. We go back and substitute here, and then here I write ID in the superscript to refer to ideal for the ideal gas. So, so we have n times n minus 1 divided by v square. V square comes because of this integral, and then you can approximate this to n square by v square, which is nothing but density squared. So, the 2 particle distribution function that we defined by keeping 2 particles at a given distance and integrating over all the other particle, that expression for ideal gas comes out to be simply rho squared. Okay. So, when I say ideal gas, it need not be a true ideal gas, it can be also a real system, provided that R1 and R2 are far away from each other. Okay. So, when R1 and R2 are far away from each other, it means that the particles sitting here and here do not really interact, okay, because the interactions could be short ranged. So, when you choose R1 R2 sufficiently long, you will see that these particles do not interact with each other. So, you can think of these 2 particles as ideal particle. So, then for such a long distance, your 2 particle distribution function will be equal to 1 by r square, rho square. So, now what I am going to do is, now that I know for a general system I have defined a 2 particle distribution function, and I also shown for an ideal gas, if this were to be an ideal gas, I know what is the 2 particle distribution function. So, now I am going to define a new quantity known as radial distribution function or pair distribution function g of r as a ratio of 2 quantities, rho 2 divided by rho 2 ideal. So, we already saw rho 2 is given by this expression. So, we write n times n minus 1, the integral. What you see in the denominator can be written simply as z, configuration integral, and the ideal part gives you 1 by rho square. So, this particular function g essentially tells us relative to the ideal gas situation, what is the probability or what is the distribution function of finding a pair of particle at a distance of r. You can already see what is the bounding limit of g of r based on this particular definition. Okay. So, let us see that you have we will choose different r values. Okay, this is r values, and then let us say this is your g of r. Suppose I take very large r values. So, r is basically the distance between 2 chosen particle, 2 randomly chosen particle. Okay. So, in this case, let us say I have a system, 2 particles are far away from here, and correspondingly there is an ideal system of the same distance. So, you can see as far as this distance r is sufficiently large, whether you have a real system or ideal system, you will see that this value of rho 2 will be equal, because in this case also, even though there is interaction in a short range, but long range, the moment you go to very long distances, these values will be very similar to ideal like. So, the ratio that we have defined as g of r will be equal to 1. So, at a far away distance, the value of g of r is likely to be about 1. So, that is our asymptotic limit. Okay, at sufficiently long separation distances, the g of r value is going to be close to 1, because we have defined g of r as a ratio between a real system and ideal system's pair distribution function. Now, what happens when you go to r equal to 0? So, r equal to 0 is a case where you have a system where two particles are sitting on top of each other. That is what it means, r equal to 0. So, we know that in real system our potential is at least hard sphere like. So, you will never have two particles sitting on top of each other, then they will have overlap, then the potential goes to infinity. So, e power minus infinity will be 0. So, and whereas for the ideal system, ideal particle can actually sit one top of each other, because they do not have volume, they do not have interaction. So, ideally you can have two particles sitting on one top of each other in an ideal system. So, the value for a rho ideal is independent of how far they are. Okay, whether it is 0 or r equal to infinity, the rho 2 ideal is always same, but the rho 2 for the real system is going to be a function of distance. So, when they are very far away, they are ideal like, so the g of r function goes to 1, but then when you come to r equal to 0, where two particles are sitting on top of each other occupying the same space, and we know through the hard sphere like potential or Lennard-Jones potential, we know that two particles cannot really sit on top of each other, because that would lead to a infinite potential energy. So, if you have an infinite potential energy, then this you basically have g of r equal to 0. So, you will have 0 up to certain overlap distance. So, typically up to r equal to sigma, the g of r value will be 0. Okay, and after that, so between these two, so these are the asymptotic limits of g of r. For very long distance separation distance, g of r will be 1. At a very close distance between 0 to sigma, about sigma, g of r is 0, and in between you may have different kind of feature that we are going to see later. Okay, so that is the physical meaning of what is g of r, or the pair distribution function, or RDF. Okay, so we use either RDF in short, or PDF, or simply g of r. So, either of these three names are used to characterize the distribution function here. So, now let us look at some characteristic of this radial distribution function, or RDF. So, this is our mathematical definition. It is a ratio of a distribution of rho 2 between a real system and ideal system. So, essentially it is a ratio of two probabilities. So, g of r is the probability of finding a pair of atoms or particles at a distance apart, r apart, at distance r apart, relative to the probability expected for a completely random distribution or otherwise ideal gas at the same density and same temperature. So, we are looking at a comparison between a real system and ideal system at the same temperature and same density, and you ask what is the probability of finding a pair of particle at the same distance r, and that is a ratio given by g of r. You can also show that when you multiply the g of r with rho, it basically gives you the average density of particle at r, that a part given that there is a tagged particle at the origin. So, the implication of this basically means, like I said before, at a far away distance from a particle, you expect the density to be average density of the entire system, okay, where density rho is given as n by v. So, if you take up one particle and you go very long distance from there, and then at that particular location the density is supposed to be an average density. So, now we know g of r at a long distance goes to 1. So, when you multiply rho with the g, then this will asymptotically reach an average density. So, that is the reason why we say g times rho is the average density at a given r. When r tends to infinity or a very long distance, this will lead to rho g r will approach rho average, whereas when you come to very close distance, because of intermolecular forces, you see a local variation of densities, okay, which we will see shortly. So, now this is a typical g of r for a liquid and gas. You can see a different signature of this RDF function for different phases of matter. Like I said before, between 0 to sigma, where sigma is the particle size, you see g of r will be close to 0 because of excluded volume effect. Whereas, when you go to very large distances, you see this g of r goes to 1, because here the particle structural correlations are completely lost. So, they are basically random distribution of particles at a far distance. a particle sitting here and the particle sitting very far away do not have any correlation, spatial correlation, and they lead to G of R value of 1. In other words, the density goes to an average density. In between, you see an oscillatory kind of behavior for a liquid, whereas for a gas, it is just a single peak and then falling down. So why you see this kind of a peak is because if you look at the representation given here, the first peak, second peak and third peak basically refers to what is the local order manifested by the intermolecular forces. So because that for example, if you consider Lennard-Jones kind of a potential, we know that there is a potential well which is the most likely paired distances. Okay, so you will see the first nearest neighbor near the potential well. So that is these set of neighbors, and after that, because of excluded volume, there are some space in which the particle cannot come. Okay, and that's why you see a dip here. These are the spaces where these spaces will be excluded by the first nearest neighbor. So you're going to have certain depletion zone where there is no particle. After that, there is a second layer of particle, but the second layer of particle is much more loosely bound than the first particle, because as you go radially outward, the range increases, okay, the distance increases, the potential basically fades out. Okay, so this particle is much more stronger in interaction with the first neighbor than the second neighbor, and so on. So that's why you can see the peak position, the peak value goes down as you go far away from the tagged particle. So in the liquid case, it's much more denser, and the neighbors feel the interaction little farther distance, because of which you see multiple peaks at some designated positions. Whereas if you look at gas, you are talking about a very dilute system where the particle will hit each other and then they move apart because of collision, constant collision happening between the atoms. So because of which you see only a pronounced peak near the collision times, and after that the particles are basically moving away. So the mean free path is quite high for gas. So you see a quick decay of the G of R function for gas. So these are important because when you do a simulation, when you calculate G of R, by looking at whether the behavior is like this or like this, you can identify whether you are talking about whether you are simulating a liquid like state or a gas like state. So G of R provides rich information about what is the phase of the matter. So now if you come to crystals also, you will see that the G of R has a very a unique signature depending upon the crystal lattice. For example, if I take one layer of FCC cubic on the left and a simple cubic on the right, you can see the atomic arrangements are a little different between the two, and this reflects in the G of R values also. For example, both are cubic systems. One is a simple cubic, other one is a face-centered cubic, but you see the relative peaks at a designated positions are quite different. For example, in the case of FCC, the peak position at R equal to 1 and the peak at R equal to 1 for a simple cubic, they look little different. Okay, so FCC has a little more value of the first peak at R equal to 1 than at simple peak. And more importantly, if you look at the peak corresponding to square root of 2, R equal to square root of 2, for FCC this number is much smaller compared to a simple cubic, which is quite high. Okay, and then you can go on to find that the peak value for R equal to 2 is quite significant for FCC, whereas for simple cubic it is little less. So by looking at the relative weights of the peak positions, you can also deduct what is the crystal structure of the system that you simulate. So both for the fluids such as gas and liquids as well as crystals, G of R provides rich information about what is the internal arrangement or local arrangement of atoms in the system. So now I want to go back to the definition of RDF and then try to write an expression that is more useful for MD simulations, the kind of expression that can be used in MD simulation to calculate, and also we try to interpret the physical meaning of coordination number using G of R function. So this is our definition of G of R, and you may recollect G of R is defined as the two particle density function rho 2 by rho 2 ideal, okay, as a ratio of two functions. So, now this what you have here, this part, the integral part, can be written in terms of sum of delta functions as well. And so what it basically means is that this configuration integral over all this n minus 2 particle could be simply written as sum over all particles delta function for the first particle and the second particle j, such that the distance between r and I and j should be equal to r. Okay, or this can be also written in a more condensed form with a single delta function, where we replace ri rj with another variable rij, which is the separation vector. And now this function, so if you look at this function, it's basically sum over I and j not equal to I, but j goes from 1 to n. And then looking at all pair that are separated by a distance of rij. So, you remember this g of r is a function of pair distance. So, from here what you can do is you can actually write this 2 sum into a 2 times half sum, where I goes from 1 equal to n, where j goes from greater than I to n, and there is a factor of 2, so that we equate these two expressions. And we also write this rij vector into simply rij, because we are talking about only the distance between the pair of particles. So, now we can ask what is the normalization of this particular quantity g of r. So, in order to do that we have to integrate this over a volume dr, and so then basically I take the integral inside this summation, and you see the integral of the delta function over dr is 1, and if you look at the number of combinations that you have is basically n times n minus 1 by 2, and then if you simplify you see that the integral of g of r dr is nothing but simply the volume of the system. Now, if you multiply density on the left hand side and right hand side, you see that the rho times the integral of g of dr is nothing but rho v, which is nothing but the number. If I have a system and then choose one particular particle and I go radially outward, and then I integrate this g of r function over this volume, okay, and that basically gives me the total number of particles in the system. Okay. So, the integral of rho times g of r dr is related to the total number of the particles. Now, this can be used to write another expression very similar to this to find what is the number of particles over a distance of from 0 to r. So, this tells you the overall total number, because this integral is from 0 to infinity, but instead of integrating from 0 to infinity, if you do from 0 to r, you can find what is the number of particle up to a distance, pair distance of r. That means, if you are interested to know what is the number of particle in a smaller shell of distance r, then you integrate this equation from 0 to r, then you see all the number of particles in this particular domain. And when you extend this r to infinity, then you get total number of particles. Okay. So, so that is an important result, because when we try to interpret g of r for first coordination, second coordination, we use this equation to find the number of neighbors in the first shell and second shell. And another important use for g of r is that it gives us the distribution of pair distances. And now we already know that many of the thermodynamic properties are given by pair interactions. So, it might be possible then to write ensemble average of pair functions using g of r. So, you may recollect, if I have a property A, function of two particles or pair distances, our usual way of writing ensemble average is 1 by q, which is a partition function, integral over configurational integral, the property A weighted by a respective ensemble distribution function. Okay, this is our usual way of writing it. So, now what we are trying to do is write the same thing, but instead of doing the integral over all the n particles, so this dr basically means integral over all the n particle configuration space. So, instead of this, now we know g of r gives the distribution function for ri and rj for the two particle distribution functions. Then this can be written over you basically integrate only between dri and drj, and then this function will take care of the rest of the n minus 2 particle integration. Okay. So, now imagine that you have a property A, which can be written as pair sum of all these small a. So, this can be, you can think of the small a as like the pair interactions u1 2 or the virial, where this would be the total energy of the system, right, where we see that the total energy is written as sum of all the pair interaction energies. So, then you can actually show that this energy E can be written as a one dimensional integral over distance between a pair of particle r. So, here r means distance between a pair of particles, provided that you have the information of g of r. Equation can be actually derived using the definition for g of r and etc., but I will skip the definition, but you can understand what is the physical meaning of these equations. What this basically means is your total energy E, let us say, is written as sum over all pair, this should be Ij. Okay, this is what our definition, and this is what we do on our MD simulations also. We go to all pairs, find the Uij and sum over all the pairs. An equivalent way of writing this is this expression. What it basically says is you take one particle and then you go to up to a particular distance of r, and then there is a spherical volume. Okay, this is a spherical volume at a distance r to r plus dr, and then there is going to be certain number of particles here, and we know this information already because rho times gr we know already is the density of particle at a distance. This is the density at distance r from a tagged particle. So, now if I multiply this by the volume of the shell, which is 4 pi r square dr, volume times the density will give you number of particles in the spherical shell. So, that means this particle is interacting with the same distance r with this set of particles around this shell. Okay. So, now you can see that now I can find at this particular distance there are so many number of pairs and multiply this with the pair interaction energy E12 corresponding to this distance. Okay. And that should give me the energy between this particle and this entire particle. Now, how many different ways you can choose this for one particle is n. So, we have to multiply by a factor of n also. So, that is this expression. N is for n number of particles, and then we multiply 4 pi r square dr times rho gr, and this a is a property that you want to average, which is u12, and then this has to be integrated from 0 to infinity. So, then also there is a factor of 1 by 2 because every time you take a particle here and you have another particle here, and then when you take this as a reference at the same distance, this also will become a pair. So, you are basically doing a double counting. To avoid this double counting, you have a factor of 1 by 2 here. So, even though this expression can be mathematically derived, but you can also physically see why this expression is correct from this particular schematic. Now, the use of such an expression is that you can write energy expression for energy and pressure using this ensemble average of pair functions by writing the total energy as a ideal part plus excess part. Okay. So, if you compare between these two, you see that this A here is written as the pair interaction V of r. The 4 pi is taken outside. So, you get 4 pi by 2 is 2 pi, and then you have n rho, and then inside you have r square dr Vg. Similarly, if you want to write for the pressure, you basically know that the pressure is given by the ideal part plus the virial, and this virial is given as minus 1 by third times sum over all the pairs of the pair virial. So, this is basically is now introduced here. So, this is ideal part as before. For this virial, we have a factor of minus 1 by 3, and then you have 2 pi n rho r square. This is a pair virial, which is nothing but this small w here is r du by dr, where this is the pair interactions between I and j. So, on one hand, g of r is able to give us information of a local structure. In the second, once we know g of r, we can even write the expression for the thermodynamic variables such as energy and pressure, as far as they can be written as a sum of pair functions. Now, more information can be obtained even for molecular systems. In the molecular systems, you have different atoms within the same molecule. Then you can think of many combination of g of r between different sites. For example, here you have site A1, A2, and here you have B2, B1. So now you can think about distribution of AB between site to site. And if you look at liquid nitrogen, which is an example for a linear molecule, and you can see that the G of R function has the same characteristic like we discussed before. G of R is 0 when R equal to close to 0, and it reaches 1 at far distances. And then the first peak is about 1.1 angstrom, which relates to the bond length within the nitrogen molecules. And after that, it's 0 because of excluded volume. And then the first peak occurs at about, second peak occurs at about 3.3, which is referred to the van der Waals radii between the nitrogen. Okay, and then you can see again there is a depletion because of excluded volume, and another peak for the second nearest neighbor, etc. So you can get rich information of the molecular details by looking at site RDF functions. So now, like I was saying before, if you integrate this G of R square dr between two limits, in this case for example you want to integrate from 3 to 5.6, you see the total number of atoms in this particular range is given by 12, which basically means the first nearest neighbor for a liquid nitrogen is about 12 atoms. Okay, and if you integrate between this limit, you will see what is the number of atoms in the second coordination shell as well. So such rich information can be obtained by looking at G of R. So here is another example for N-butane. So N-butane, you have CH, you have basically carbon, hydrogen, etc. So this is a distribution function for G of R for C and C. So you take carbon atom from here and take another carbon atom here, take different combination of such carbon atoms, and then you find what is the probability of finding the pair distribution for carbon-carbon. So you can see the first peak corresponds to carbon-carbon backbone distance, and then you get range of multiple peaks, which is quite complicated because for butane it actually exists into different conformational isomers such as trans, gauche plus, gauche minus configurations, because of which you get these multiple peaks. All these peaks could be related to molecular structure and isomorphism. And if you look at for water is modeled as one oxygen and two hydrogens with a fixed bond and bond angle, and you can see the G of R for between oxygen and oxygen. So if you think about two molecules of water, you can see what is the pair distribution function for oxygen and oxygen hydrogen, and also between hydrogen and hydrogen. Okay, so you can see the first hydrogen shell, second hydrogen shell, and similarly for the HH. So you can get all this information from a molecular system, and you can construct what is the local order of water molecules based on these informations. For instance, if you look at all these numbers at which the first peak, second peak occurs for all these distribution function, you can construct that the water exists in a tetrahedral coordination because of hydrogen bonding in the system. And you can also integrate from 0 to 3.5 here to find what is the first nearest neighbor for water. You can see that there are about first 4, so that basically proves it is a tetrahedral order. Now, one final thing about the G of R is that it is also related to what is known as the structure factor, and the structure factor is something that is obtained in neutron and X-ray scattering experiments. So by looking at the relationship between G of R and S of K structure factor, we can also compare our G of R value with the experimentally measured structure factor. So the structure factor is actually defined as a function of number density. So the way to think about structure factor is in MD simulation we think about individual particles and particle positions, but another way of looking at is thinking about the particle distribution as a set of waves with a particular wavelength. So the number density is written in terms of a wave functions, and then you look at what is the correlation of these number densities or the fluctuations in the number density of and then you can show that again I'm skipping all the derivations to show that this structure factor at a given wave number is related to the integral of the G of R function. So this basically tells you that if I know G of R, I can get S of K, or if you do an inverse Fourier transform, you can also say if I know S of K and I can find what is G of R. So through these two equations we can actually hope to calculate G of R from our simulations and then compare with S of K measured from experiments. And one final use of G of R is also to show that you can use it as a first guess for the pair interactions. For example, the G of R can be approximated to exponential of minus V by kBt, where this V here is the pair potential. And then if you invert it, which is known as Boltzmann inversion, you can get an effective potential, okay, as minus kBt ln of G of R. And especially when you do coarse graining of simulations, what one can do is you do first an atomic simulation and then get G of R. From there you get a pair potential between a pair of sites, and then you can use this as an effective potential as well. So these are multiple role of G of R in MD simulations. To summarize, we see this RDF characterizes local structure of materials, the local order, the range of order, everything can be obtained, and then it is actually useful to identify different phases of matter, because whether it is a gas or liquid or solid, the signature of RDF is quite different. By looking at the periodicity and the coordination number, we can also identify what is the local structural information of the matter. For molecular system, the site RDF is quite useful, and that allows us to understand what is the local atomic arrangements in a molecular system. And more generally, RDF can also be used to calculate thermodynamic quantities of pair functions, for which examples of energy and pressure were shown. And RDF is also related to the Fourier transform of experimentally measurable structure factor as well.